it's now almost 6 years ago that I joined TNG as a theoretical physicist fresh from university. And well, I had the great luck and pleasure to be assigned a project and work closely together with Konstantin. And right from the start, he was always a role model for me, and I learned a lot from him. So I'm very grateful to have him here today. Nowadays, he's working at a very interesting place also, Ververica, which is the company founded by the creators of open source stream processing framework or tool, Apache Flink. Konstantin is the head of product there and responsible for developing all kinds of interesting stuff. One of them is a new cool thing the folks at Ververica and I guess the broader Apache Flink community has come up with, which is called Stateful Functions, a framework which strives to revolutionize how we think about architecture in some respects. And we are looking forward to the insights that Konstantin has to share about those today. Small organizational issue. I mean, we are living in interesting times, so this is a hybrid event. Not only do we have a live audience in this room, but people are also watching via Zoom or via YouTube. For all of those who have joined remote, you can also ask questions in a dedicated Slack channel. And then at the end, there will be a QA session where we can get into those. So please, Konstantin, it's your turn. Join me in welcoming Konstantin to the stage.
Yeah, thanks a lot for the kind introduction, and thank you, TNG, for the invitation to speak here. I'm Konstantin Knauf, and yeah, just before I start to talk about stateful functions and in the context of microservice architectures, let me briefly introduce Ververica. You've already done that basically. So we're the company founded by the original creators of Apache Flink, which is one of the most active Apache projects over the last years. We also have a commercial product that adds services around Apache Flink called the Ververica Platform. And for about 3 years now, we have been a subsidiary of the Alibaba Group. Mostly Berlin-based company. So I want to talk to you about microservices and what stateful functions can bring to microservice architectures. But let me say I'm not, well, arguably I'm an expert in stream processing and Apache Flink and so on. I'm not the greatest expert in microservice architectures. So please take my general considerations around microservices and architecture with a grain of salt. It's certainly my perspective on the topic, and there are other people who know a lot more about that topic. It's also a very wide field, arguably. So why do people do microservices? There are a lot of reasons, and I want to look at a few of them. One reason is scaling. So if you put all your services into one monolith, you need to scale them to the same scale. You need to scale them in the same way. So basically everything is one Java application. All your services get the same resources and you have the same number of instances of each service. If you deploy them more in a more fine-grained way, each service for itself or multiple services together, it doesn't really matter. You can scale them differently. You can scale them out, you can scale them up depending on what this service needs. Each service probably has different resource requirements, and for them, some of them it makes sense to scale them up. For others, it makes sense to scale them out. And some of them are CPU bound, some of them are maybe memory bound, and you can take that into consideration. And overall, you are more resource efficient and you save some money. And probably the system overall also becomes more scalable because the individual smaller pieces can be scaled out more easily. So that's one reason. Another reason might be independent ownership, independent life cycles, independent releases for each microservice. So instead of a lot of teams working on a shared monolith, or that releases all services together. You can release each service independently. They can have different iteration cycles. One can move faster in an area where there's a lot of innovation. Another more mature area of the overall system can move slower. And overall, you hope that you innovate faster, that you can go to market faster, because each individual piece can release once it's ready. And the ownership in the teams also, well, maybe helps motivation and quality, because each team really feels responsible for their small artifact, their small deployment, their service, and it's not everyone contributing to the same anonymous monolith. And you can use independent tooling as well. So you don't need to use one programming language, one deployment pipeline. So each team can use, or each service can be written in the tool that is the best for that tool or for that problem at hand. So not everything needs to be Java, for example. It can be JavaScript for some services. It can be Java for others, Python for others, and so on. That increases developer efficiency, maybe also increases developer happiness. And talking about developer efficiency, each individual developer also needs to know a smaller code base, so they become productive more quickly because they don't need to learn that much. There are a lot of caveats and a lot of ifs. It's, I guess, always if you do it right. But that's the promise, I would say. So overall, it's more scalable and resource efficient. You get faster time to, or lower time to market, faster iterations, and your developers are more efficient and more happy. Perfect. There's a caveat. So let's look at what microservices actually change. So in a monolith, you maybe have service and then the shopping cart service. And that shopping cart service, once someone wants to place an order, needs to call the order service and place that order. And in a monolith, although that doesn't compile, you can just call the other service and that's it. How does that look like if the shopping cart service and the order service are different deployments, different artifacts? Probably something like that. You have the shopping cart service that is deployed with its own database, and you have the order service that is deployed with its own database. And maybe it's via an HTTP post call to create an order that the shopping cart service calls the other service, and then it returns a success status, the order ID, some kind of reference to the order that was placed. Could also be done differently, of course. That is just the simplest way to do it synchronously via HTTP. Could also be a queue, could also be some kind of asynchronous polling. Slightly different characteristics, but fundamentally the same. Fundamentally, I think what I'll talk about afterwards applies to the, regardless of the messaging protocol, if you will. So what changes now? Things. I think most importantly, these things can now fail independently. So instead of basically just the whole monolith with its database going down, or without its database, hopefully, and everything stopping at the same time, and then you have database transactions, and that makes sure that everything stays consistent. So if your monolith goes down, all pending transactions are aborted, you restart the application, your database is in consistent state, you continue. On the other hand, if you have microservices, usually only parts of the system fail. So for example, the shopping cart service tries to call the order service and doesn't get a response because the order service has failed. But the shopping cart service can continue to make progress, theoretically at least. Or it tries to make progress at least. In addition to that, they not only fail independently, but they also don't know about each other's failures. So the shopping cart service tries to place an order, it gets in timeout. Maybe the order service has failed, or maybe its database has failed. But maybe it's just the request that got lost, or the response that is what got lost. And actually the call was completely successful, you just don't know about it. And maybe everything is actually fine, it's just very slow. And you think it's failed because it has timed out, but actually everything is working fine, it's just garbage collecting. And actually in a distributed system, there's no way to distinguish a very slow machine from a system that is down. I'll talk more about the problem of independent failures in more detail later, but I think this overall, this is the biggest issue with microservices, that you have independent failures, and in the presence of independent failures, it's very hard to get close to the consistency guarantees that a monolith can provide to you. When I say consistency guarantees, what do I mean? I mean being able to produce correct results in the presence of failure. So if you don't place an order twice, you still have the right number of inventory items in your inventory service, and you haven't like double counted a shipment, things like that. You want correct results in the presence of failure. That's what I mean with consistency guarantees. So well, what do you do then? There are a lot of techniques to solve this. You could do retries, you have circuit breakers, you have distributed transactions. There's the saga pattern if you don't want to do or cannot do distributed transactions. You try to make everything idempotent so that you can just retry without harm. You can put persistent queues in the middle like Kafka. You can make everything asynchronous so that you don't need to wait so long and you don't get as many timeouts. You can like add a lot of complicated things to make this or to work around this problem of independent failures and retries and timeouts. When you make a call over the network, you also add latency and overhead. So if I just in my Java application call the other service, then this is all in memory. It's fast. If I call the other service over the network, then there's the network latency and then round trip costs, but there's also serialization. So you cannot just push it over there via memory. You need to serialize it. You need to deserialize it. And if you have a lot of data, that is extremely expensive. There are also solutions for that. gRPC, maybe you can do everything asynchronously. Then it's also a little bit, you work a little bit around the latency, or the latency doesn't impact your throughput as much anymore. There's Apache Arrow, for example, which stores data in a format that it can be efficiently mapped to memory again. Again, there are solutions, but you need to think about it. And microservices also need service discovery. You need to know where the other service is, and you need to know how to reach it, under which IP address. You need to know if you have multiple services, they need to be load balanced. Maybe if you want to do deployments, you have dynamic routing to new instances, and so on and so forth. Also, again, you deploy everything on Kubernetes because Kubernetes makes that easy, but it also adds complexity. You deploy a service mesh because that solves a lot of things, but it's a service mesh. So now you need to know what a service mesh is and how it works. So again, there are solutions, but they also add complexity. So it's not everything is sunshine. Consistency becomes hard. You need service discovery. You have lower performance or higher overhead for messages or for calls between services. And debugging and then monitoring is hard. I haven't had a slide for that, but you can imagine that if you need to trace errors through multiple services and need to find out what is actually going wrong here, then this also becomes harder if you need to look at 10 services that one request touches compared to one service. There are also solutions for that, open distributed tracing and so on, but again, complexity. If you're thinking microservices, what about serverless or functions as a service? How does that relate? I think it's basically like all the advantages are even better and all the disadvantages are even worse. So there is the managed nature, and you have even more fine-grained scalability, and your deployment units are even simpler, and but consistency and retries and all of that becomes even more important, because now you're even paying for the wait time that you wait on other services. So it's even more important that you make everything asynchronous and that you put queues in between. And yeah, actually you don't have a database, so you need to also take, let's say, DynamoDB, a serverless database, but then this database also needs to be scaled, and that's actually not as easy as scaling a Lambda. So I think you get all the advantages even better, but you also get all the disadvantages in an even worse way. So I think most of what I'm talking about microservices also applies to a function as a service-based architecture with a serverless database in a similar way. So what my promise or the promise of stateful functions is basically that we end up with this picture, that we don't give up on the advantages, but consistency becomes easy. Service discovery is not required anymore, and well, the lower performance we can argue, and debugging and monitoring arguably is still hard. So the silver bullet, stateful functions. Well, we'll talk in the end. We'll also talk about whether that's actually true and what the caveats are. But yeah, for now it's a silver bullet. So what is stateful functions? It's part of Apache Flink. Apache Flink overall started and is still most popular for stateful stream processing at scale. So that's the part in the middle. Over the last 2-3 years, we've expanded the application space of stateful stream processing to other areas and applied the principles of stream processing to other areas. So on the left, or yeah, on your left, there's streaming analytics, Flink SQL, so streaming SQL, batch stream unification. So basically bringing stream processing more to the analytics and the offline space. And on the right hand side, there's stateful functions, which is our topic today. And that is about bringing the paradigms of stateful stream processing to general event-driven applications. So let's go back to the consistency problem of microservices. We have 3 microservices here, or first of all, 3 microservices, classical 2-tiered architecture. So we have an application in the compute layer, and we have a database in the storage layer and the persistence layer. And each application has its own database. Now, what happens here if a request comes into application 1? Probably it first goes to its database, collects some data about the user, for example, that the request is about. It gets this data, then it realizes, okay, actually I need something from the other service to serve this request. So it calls the other service. The other service goes to its database, collects some data, gets that back, sends it back to application 1, and then application 1 can send out the result. Now, just to reiterate, what happens if application 1 doesn't get a response? Well, it needs a response to return to the user. So it now basically needs to ask again, but depending on what happened, this is actually difficult, because if application 2 has gotten the request, then calling again might lead to a duplicate. If this is the inventory service and it's deducting from the inventory count, then you don't want to deduct twice. So should I actually send it? Should I not? But you don't know. So in the end, the only thing that you can do is to retry, because you don't know whether that failed or not. So application 2 actually needs to be able to handle retries all the time, because basically every request could potentially be retried because it seemed not successful. So one way to do that would be to make everything idempotent, so you can do the same thing twice and it doesn't change the result, which makes the whole thing a little bit more complicated, but it's also not solving everything. So you still at some point need to need to stop retrying, right? Because if that is, and return an error to the user, then you still don't know in that case where you have stopped retrying whether that was actually successful or whether the first one actually succeeded and afterwards everything went down. If you're calling multiple services, maybe some services have succeeded, others have not succeeded, and now you actually want it to be one transaction. So you need to roll back the payment because the shipment service has not responded. So every service also needs to be able to roll back your requests. So there's quite a bit to it. Now, let's think about, could we do that differently? What if not the application handles messaging, but what if the database actually handles messaging? So the request actually comes into the database. And now the database knows for that kind of request, I need to call application 1. And with basically the database gives application 1 the request and the data that is scoped to that request. Application 1 can do its stuff and wants to call application 2. So it sends a message back to the database with the request to application 2, and the database sends the message to application 2, and application 2 gets its data from the database along with the request from application 1, sends back to the database sends it back to application 1 with the response from application 2. Application 1 does its final thing and sends it out. How is that different? Now, if here, for example, a message gets lost, then the database, the persistence layer is aware of it because the persistence layer is the one that is responsible for like routing the messages and these things. So if the database realizes something has gone wrong, it can roll back everything. It can roll back the message itself, and it can roll back the state changes, the database changes that were related to this message. So because the database is responsible for both messaging and the state, it can always keep it in sync. And you might have guessed it, that is what stateful functions basically is. It's the database that handles messaging and state at the same, in one piece, and by that simplifies this or solves this consistency issue. More specifically, stateful functions consists of functions. So the fundamental building block that you as a developer interact with are functions, and functions represent small pieces of logic, usually as entities. So you have one function that represents a user, one function that represents maybe an order, one function that represents a product. And the functions can be invoked via messages, like a services. And as long as a function is not invoked, it doesn't consume any resources. Maybe similar to a virtual actor. So you don't have, let's say, one object per user on the heap, if you will. The functions can be implemented in any language that can handle HTTP or gRPC. Stateful functions itself comes with SDKs for Java, Go, and Python. And there is a Node or TypeScript SDK in the next release. I think one of your colleagues has actually contributed to that, or one of the TNG colleagues. Functions can message each other arbitrarily. So a user can message products and so on. And they can do that dynamically during the runtime, which actually is nothing special if you come from a microservice world, or if you come from the stream processing world, where usually everything is a pre-compiled graph, then that is something worth mentioning. And they address each other by logical addresses. So the user max messages the product toilet paper and doesn't need to know where that function is deployed. Every function has consistent local state and as in form of a key value store, basically, for arbitrary types. And you get out of the box exactly once for state and messaging. So you are guaranteed that you see every message exactly one time, that your state is always affected by each message exactly once. And you even get ordering guarantees within one product. So one product sees all messages that go to that product in a deterministic order that doesn't change if there are failures anywhere in the system. For all of that, you don't need a database. So the stateful functions, I'll mention that again because I think it's very, very important. The stateful functions cluster itself is stateless. So it doesn't need any disks, basically. The only thing that you need is some mass storage. So HDFS or S3, something that is cheap, it's extremely durable, and it's widely available. And that is basically all that a stateful function cluster needs for durability. You can remove nodes and add nodes to a stateful function cluster arbitrarily without affecting durability guarantees. That is, for example, it's very different to most databases that work with replication, where every node basically stores a replica of some shard of your database. And if you bring down a node, then or if you bring down enough nodes, then basically data is lost. And you actually need to care about the durability of your disks. That's not the case here. Yeah. So let's look at how you implement a stateful function. We'll start with Python, or mostly look at Python. So this is a simple stateful function that receives messages in the form of names, and depending on how many times it has seen this person, it greets the person differently. And well, we need to import the SDK, of course, and then the signature of a stateful function is basically always the same. You get a context and you get the message itself. And then, well, in this case, we know the message is a string and it's just the name. So we get the name from the message. And then we get this storage from the context. And the storage is basically your database. But you interact with it like it was a hash map or like an in-memory map, basically. You get the storage. From the storage, you can take the current scene count, or if there is none, then it's 0 because you haven't seen that name before. And then you set the scene count to scene +1. And that is basically all you need to do. And you get exactly once guarantees for that state, and it's durable and everything. You see that this scene count needed to be registered, if you will, before. So you need to declare for every function what kind of database schema it's basically working with, because then the database knows what, let's say, columns or what tables it needs to supply this function if it's invoking that function. And afterwards, we send a message to another function, and here you see the names of the functions, so that, or the function type. One function is called the greeter in the COM example functions namespace. The other one is called the inbox, and well, the target ID is the name. We'll talk more about the address in a second, and then just the content, which is just this greeting. And that's all it is, basically. In Java, I don't want to go through this again, but I just want to point out that the concepts are exactly the same. So there are some language specific differences because Java just works differently than Python, but you have a value spec, you have the context, you have the message, you have the storage, and the SDKs work exactly the same in the different languages. And if you know the concepts in one SDK, you know them in the other. I want to talk a little bit about the AddressScope storage because I think that's important to understand. So an address is the address of a function, and it consists of the type name, which was greeter or inbox, and the ID, which in our case was the name. Could also be the type product and the name toilet paper, or the ID toilet paper, or yeah, user Max. And then the address scoped storage is a key value store for arbitrary types. So you can put in, don't need to put in strings or integers, can put in any type that, if it gets complicated, you need to specify the serializer and deserializer yourself. But generally, you can put in anything, and you can take something out, you can remove something, you can put something, and it's always scoped to that particular user. So that is one limitation, that if function max is invoked, it cannot interact with the data that is stored under the key Konstantin. It can only interact with its own scene count, but it doesn't know how often I was seen in the creature. So that limits to some extent the kind of applications that you can build. So for example, an application that calculates the statistics, how often people were seen in general, it's probably a little bit difficult, because it would need to basically interact with the whole column of that database and not just with a few rows. So it's good for OLTP transactional applications, not so good for analytical OLAP applications that need to access full columns. You can also send messages out of stateful functions through an egress. This is now Go. Again, you see it looks a little bit different, but there's again the context, the message, and so on. And just instead of sending something out to a different function, you send it out to Kafka, for example. So the ingresses and the egresses, which is the way you get things in and out of stateful functions, are usually message queues. So out of the box, we support Kinesis and Kafka, maybe Pulsar by now as well. So usually message queues, because it's important that we can replay messages. That's part of the way the fault tolerance works. So you cannot directly send a message via HTTP to a stateful functions cluster. It needs to be persisted in a queue first. So how is the whole thing deployed? Because, well, microservices is first and foremost about deployment, actually. So reminder, this is how it looked like. We have stateful functions and we have our stateless microservices. And the stateful functions cluster needs to call the different microservices, and it needs to know where which function is. And the way that is configured is via the configuration of the stateful functions cluster and via an endpoint configuration. So you see basically all functions in the com example namespace can be reached under, well, this pattern, some host name and then / the function name. How does that concretely look like? So for example, on Kubernetes, if you would put each of your functions in a deployment, or you can also group multiple functions together, it doesn't need to be every function separate deployable. If you put all of them into a deployment and behind a service in the example namespace, then the pattern could be all your functions in the example namespace are reachable via the function name .example.service 80. And then the nice thing about that is that, well, that is nice, that again, a reminder, your Apache Flink class, it's also just 2 deployments. You don't need any persistent volumes. You don't need stateful sets. So all that more complicated operational stuff of Kubernetes is not there. It's just 2 stateless deployments with S3 or something else that gives you mass storage. So the nice thing about this definition and the template is that if you add a new function, you don't need to change anything in the database. You just deploy a new function. You put the annotations on it, what kind of state it has, what kind of tables it needs, and the stateful function cluster will adapt to it. Basically, the first time that this function receives a request, the cluster doesn't know what kind of tables it needs, so it will the function will ask for it, and from there on, the stateful function cluster will know what kind of tables it needs to send to that function. And that's also the case for existing functions. If you change the state schema that a function needs, then you just change it, you deploy it, and your stateful functions cluster will from there on only send those tables or those values to the function that that it has registered with this value spec. And another example, if you deploy each of the functions as a Lambda or as an Azure function, then it could look like that. You basically put all your functions into Lambda, or you can again put multiple functions into one Lambda if you want to deploy them together, and you put them behind an API gateway. And then you have in the URL path, you have the gateway / the function name. And again, you can add and remove functions behind that gateway without touching your stateful functions cluster. And for that example, there's actually, or I've built a full running example with all your Terraform stuff that you need to bring this up on GitHub for another talk that I gave in the past. It should still work if your Terraform version is old. Yeah. Of course, you can also do something heterogeneous. So you can put some deployments in your Kubernetes cluster or some functions in your Kubernetes cluster. Then you have this one function that is very compute intensive and needs to scale very dynamically. So you put it into a Lambda. And then you have also some functions that you have added to a legacy application that you still have on premise in your application server. And you put them into the same stateful functions cluster. And then you just have a couple of endpoint specifications, but that doesn't change anything about the consistency guarantees. So you still get exactly once messaging and state between all these different systems, which is quite impressive, I think. And if you, there's even one thing that goes beyond that, I think. Stateful functions, I told you, as basically S3 as the backend for its state snapshots. So every few seconds, the cluster will perform a snapshot of the whole distributed state and put it to S3. So there you basically now have kind of a distributed heap dump of all your applications, regardless of where they are deployed. And you can now actually take this distributed heap dump or state dump that represents the state of all these applications, and at a logical point in time that is consistent. All applications have seen the same messages and haven't seen the same messages, and can start analyzing that, which is quite a unique property, I think, that you don't get from other systems. It's very hard to get a consistent snapshot of the databases of applications that are deployed in such a distributed way. So is this too good to be true? So let me show you the tweet that actually inspired that talk, or that look, or that perspective on stateful functions. So it was, if you don't need to scale out and don't need to separate failure scopes, then why are you splitting two pieces of code into microservices where you're introducing more failures and now reduce consistency guarantees? So I talked a lot about the scale out, but I kind of neglected this don't need a separate failure scope. So actually, this should probably look like this. So smaller failure domains is not just a nuisance of microservices, it's also a feature of microservices. So the fact that parts of your system can make progress while other parts failed is actually something that you want in some cases. And I've just didn't tell you. And that is something where stateful functions is not, or where you actually get this if you take stateful functions. So you get the consistency, you get the service discovery, but now the failures are more coupled again, because if one of your functions that is talking to one stateful function cluster stops responding, then the messages pile up and this queue is limited. So at some point, everything will stop. And the cluster will wait until this one service comes back and starts answering again. And then the whole system will continue to make progress. This is something you need to be aware of. It's basically you lose that property of microservices, but you get the consistency and the service discovery. So basically, as said in the tweet, if you don't need independent scale out and failure domains, it's actually if you need the independent scale out, if you need the fast iteration, if you need independent tools for different services, but don't want the consistency, and you don't want the small failure domains, I guess. So what is a failure domain actually? Or we actually haven't talked about that a lot. So it's basically if parts, it describes if one part or device or service fails, what is the area that is affected by this failure? It's, I think, traditionally more on the hardware side. So if a router fails, or if a data center fails, or if a network fails, what part of my data center, of my infrastructure is affected by that? But you can, of course, also look at it from a services perspective. How many services or which services are affected if one of my services fails? Yeah, here it's forest fires. Also failure domains, basically. The street and the fire line there is the boundary of that failure domain, I suppose. So what failure domains do you usually want? Or I guess it's highly use case specific, but if we think about our example here with the cart service, the shopping cart service, and then we have the whole like order fulfillment process with the order service, which orchestrates shipment, payment, inventory, and there's probably a lot more that I'm not aware of because I'm not in retail. Well, technically, somehow I am, but not really. What do you usually want? Probably, or maybe you want something like that. So the cart service should always work because that will enable people to continue shopping, continue to put things into your shopping cart. And then it becomes a little bit more sketchy or unclear, I think, on the right here, because do you want that your orders go through if you cannot change your inventory, or if you cannot pay, or if you cannot ship? Or is it actually good if one of those things doesn't work, if you cannot fulfill any orders overall? They basically just are being, they're basically just being, queued here. And then once all the services on the right are available, then you just fulfill all your orders. Is that actually an acceptable behavior that is worth simplifying your architecture? Maybe shipment I took into a separate one here, but I'm not sure about that actually. I also have a picture that is like this, because the shipment service probably interacts with a lot of like real world stuff that fails in different scenarios than the software. So maybe that is worth putting into a separate failure domain or not. I don't know. So basically, if you work with stateful functions, you need to think about that a little bit. What do you want to put into one failure domain? What should fail together and what should fail independently? And then use one stateful functions cluster, a couple of Docker containers basically, for each of those failure domains. And inside those failure domains, you then get the guarantees, and outside you still have to work with queues and yeah, basically don't have this consistency guarantees. Yeah, so sun shines a little bit. So you basically need to think about it, and then you need to, and my hypothesis is that in a lot of scenarios, it's actually not too bad to that everything fails together, or it's a valid trade-off to let things fail together, because it doesn't make sense that things fail independently in a lot of cases. Yeah, and yeah, that is kind of my conclusion for this talk, or the value proposition of stateful functions. If you found that interesting, try it out. Try out stateful functions. You can also try out Apache Flink, but I haven't talked about that, or Apache Flink Classic. Help us improve it. You can contribute to docs, codes, tutorials. You can talk to, if you're at TNG, you can talk to Ingo or Nico Weidner, who are both working on Apache Flink in their projects. You can join meetups, and most importantly, we have also our conference coming up. The last time fully virtual in October. It's free, of course, as most virtual events. And there is a dedicated stateful functions track for the first time. We have use case talks by Reddit, Nordstrom, which is a retailer, US retailer, Finicity, FinTech, and of course ourselves and a few others. And there are also tracks on Flink SQL, batch stream unification, Flink operations. So basically these other pillars that we've seen on that one slide. Yeah, that's basically all I wanted to talk about today. I think we have a bit of time for questions, and thanks a lot.
Yeah, thanks, Konstantin, for this these very inspiring insights. We have time for a few questions. I think I saw already some. Okay, let's start here.
Okay. Yeah, so about this stateful functions cluster, because I experimented a bit with this stuff and didn't get it. Like, is it just a standard Flink cluster? So could I use, for example, a Ververica platform, or do I need something special because the containers in the tutorials are they have some additional stuff?
Yeah. So basically, stateful functions is a standard Apache Flink cluster that is running one dedicated job, basically. So it's the stateful function is basically a Flink job. Yeah, so you can use the Ververica platform. There are some limitations though. What you can do. I think it will probably diverge a little bit in the future, or hopefully it will diverge a little bit in the future between stateful functions cluster and the Flink cluster, in the sense that, for example, for Flink cluster, you always need a job manager and at least one worker. And it would be nice if a stateful functions cluster in its minimum configuration is just one container and one process that fulfills both roles. So, and I think we also want to change the standard configurations quite a bit in a way that we're not optimizing for like super high performance, super high throughput in the case of stateful functions, but more on the conservative defaults that just make it work in most cases. And maybe performance on the Flink side is not as important because you anyway have the network overhead. So you basically anyway need to go over the network, then you have your slow Python thing, then it doesn't matter like that RocksDB, so the state backend of Apache Flink is a little bit slower, but more robust. So in essence, it's a Flink cluster, but I think it will change a bit and that it's more specialized Flink cluster.
Okay, thank you.
One more question.
Thank you for the talk. So if I got you right, as an ingress, you always need some kind of persistent queue. So would it, for this example with the shop, also be possible to call from the user application some HTTP endpoint and to place the order? Because as a user, I imagine in the browser, I just sent the request, or how would you imagine this one?
So no, that doesn't work. So there is no HTTP ingress. They have always been thoughts about adding that, but it's not very easy because you need this replayability for fault tolerance. You need to be able to replay a request. So in some sense, the stateful functions in terms of the use cases that it's right now most suitable to are asynchronous ones. So ones that are not directly in a synchronous user flow, where the user is waiting for the request. The reason for that is also that in the Apache Flink cluster, when it restarts, it needs to replay messages, right? And we're not at the point yet where we can make these state snapshots at consistently at 100 milliseconds or so, like way below 1 second. It's the vision, and maybe we're there in a year or so. But right now, you probably do state snapshots maybe every 10 seconds or so. And that means if there is a failure, you need to replay messages of 10 seconds. So your latency is probably, or your tail latencies are in that area, which is not acceptable for an end user facing synchronous interaction. So yeah, it's more in the asynchronous tier of your overall architecture, I would say, right now.
I think I saw a few questions in the Slack channel, and Gerhard can. Do you want to read them?
So the first question is, can a stateful function have multiple ingresses or egresses? And can you maybe even define a possibility space so that you can send a message to one egress if one condition is met and to another egress if a different condition is met?
Yeah, so the first question, ingresses are basically defined per ingress to which function those messages should be sent. So you define your ingresses and you say everything that is coming from that ingress is supposed to be sent to that function, and this is how you determine the ID of the function that you send it to. So yes, you can say basically for every ingress that you define, you can send it to the same function if you want to. So a function can have multiple inputs. And one ingress can also send to multiple functions, I think. The other question, can I send to multiple egresses depending on some logic? Totally. You can put arbitrary code in your stateful function. It's just a function, just a Python function, just a Java function. You can do anything in there. It's a typical pattern that one function receives different types of messages, for example. So usually you do some pattern matching at the beginning where you distinguish based on the message type that you have received, and then have some specific logic. And then once everything has come together, you, for example, send out a final result. One example or one demo that we have in a few talks, for example, is a machine learning or a feature assembly function where you get a financial transaction, and then this one function calls out to a couple of other functions to add features to the feature vector. And once it has received the results of all the other functions, it sends the final feature vector to the next function. So that would be one example of such an interaction. Basically, you can think of a function as an actor with state that you don't need to worry about. And that is persisted.
Cool. I hope this answers the first question I saw on the Slack. Another one is from one who's in the audience, so they can ask themselves.
Yeah, thank you for your talk. My question is, how is changing signatures of a function handled? Because you might have different versions of modules, whatever, and you probably don't want to have the same version everywhere.
Yeah, it's a good question. So, I mean, the signature of the function or the method in the language itself is always the same, right? But basically, the question is, what if the message types change that it receives or sends out? It's basically up to the user to handle that. So what we use more, or where the format that stateful functions has the most support for is protobuf, because protobuf is language agnostic by default, and we need serialization or our default serialization needs to work in all the SDKs. And protobuf has some support for some ways of changing the schema, and that's probably the first thing that I would recommend, to fall back to that and basically evolve the protobuf types in a compatible way, and then protobuf handles that. Otherwise, you need to add actual logic into your functions that handle those compatibilities.
Okay, I guess we have time for one more question. Okay, then I have one. I mean, one of the upsides you pointed out for microservice architectures is basically developer efficiency, developer happiness. It seems from the conference announcement there are already some adopters of stateful functions. So maybe if you can, are there some stories you can tell, or some experiences how teams actually adopt this kind of what seems like a very convenient way to write applications?
So I don't know too much about. I've talked to most of them once or twice, but I don't know too much about the use cases. The use cases is super diverse. Because it's very general purpose framework, so the use cases are also quite diverse. I think most of them really look at it from a, okay, this is like Akka, but I have persistence without a database. And so I don't need to worry about that part. Yeah, and yeah, the use cases, admittedly, they're not core business use cases at that point, right? The system is 1 year old. You usually don't start to like change your central payment system of the retailer to a brand new technology. So they're usually not core systems, but yeah, very different, very diverse. A lot of them are in the area of yeah, basically state machines or modeling some kind of stateful workflow where a lot of different services are involved or a lot of different steps need to be done and need to be called out to. And you want to basically persist the state of this workflow. And yeah, each of the steps is mapped to one function. And so these like state entities or state entity modeling, state machines, this is something that we see yeah, frequently.
Okay, thank you for the inspiring talk, Konstantin. Let's give him a warm thank you.